Today we will start the pharmacology, and the book I'm using is the preclinical pharmacology from Kaplan. So let's get started. First of all, the basic two mechanisms uh, underlying the pharmacology are pharmacokinetics and pharmacodynamics. And the first chapter is regarding pharmacokinetics. So let's get into it. The definition of pharmacokinetic is that the effect of body on the drug. It is in simple words. It means that how the body react when the drug is administered to it. So let's focus on the diagram. Um, Okay, the drug administered, it can be intravascular, it can be intravenous, it can be intramuscular, and when it is administering, it absorbed into the plasma, and from the plasma, the distribution of the drug occurs. It can be either to the tissue storage or to the site of actions. Okay, and the site of actions basically is pharmacodynamics. It is not pharmacokinetics. The drug metabolism, as far as liver, the lung, and blood are concerned, these are the sites for the drug metabolism. And drug excretion, it can be either through renal or biliary system or via exhalation through lungs. So these processes like absorption, distribution, metabolism, and excretion, these are under the pharmacokinetic principles. The other term which is used is biodisposition. Biodisposition means that the permeation of the drug across the biological membranes, the plasma membrane. So the first step is the permeation. Apart from the administration, the ways of administration of the drug will directly go through the permeation. Permeation depends on three factors or three factors which affect the permeation. First is the solubility. Solubility, it means that how effective the drug can diffuse through the lipid bilayers. The lipid bilayers, as you know, consist of the phospholipids, and they consist of hydrophilic head and hydrophobic tails. This is the hydrophilic head and hydrophobic tails, and through that, and it consists of lipid bilayer, phospholipid bilayer. So the solubility of the drug is a major factor as far as the permeation is concerned. The second thing is concentration gradient. You know that the molecules go from higher concentration to the low concentration. So the concentration gradient, the diffusion down a concentration gradient, it includes free and ionized drug forms, because the bulky or ionized drugs are more prone to not undergo the concentration gradient. Okay, the third is the surface area and vascularity. The surface area, the example, for example, is the stomach vs intestine. Stomach consists of less surface area, and intestine is more uh, has more large surface area, and also has the larger vascular supply through the arteries. So the permeation also depends on the surface area and vascularity. Three factors: the solubility, concentration gradient, and surface area. The second important thing in the pharmacokinetics is the ionization principles. Ionization principles, let's talk about in detail. The drugs can be either weak acids, the some examples I will discuss in a minute, and they can be either weak bases. And these exist either in non-ionized form or can be present in ionized form, and it depends on the pH of the environment whether the drug can be present in ionized form or it can be present in unionized form. It only depends on the pH of the environment where the drug is present currently. pKa, it is a very important term. The pKa is defined as the pH the pH at which the drug is 50% ionized and 50% non-ionized. It means that, for example, a pKa of a particular drug is 5. It means that at the pH of 5, the drug is 50% ionized and the 50% of the drug is in non-ionized state. As you know that the biological membranes, plasma membranes, these are lipid bilayer constituents. So only non-ionized, which means that uncharged form of the drug, which is not charged, which does not carry any charge, is more permeable to cross the biological membranes, and the ionized forms which carry a charge. Okay, these are not crossing the biological membranes because they become bulky. Just think of that, when the charge is attached, the drug become bulky. So for memorization purposes, but it becomes more water soluble, and it is excreted through the renal system. So what is ionization? It means that the pKa of the drug is the pH at which the drug is 50% ionized and 50% non-ionized. And non-ionized form are more likely to cross the biological membranes than ionized forms. So this is an equation, and just go through this equation and you will be cleared how the interlinked between ionized and non-ionized form. Weak acid. The examples of weak acid include aspirin, which is also known as acetylsalicylic acid, antibiotics like penicillins and cephalosporins, and thiazide and loop diuretics. These are weak acids. There are a bunch of examples, other examples, but these are in high yield to know. Aspirin, penicillin, cephalosporins, thiazide, and loop diuretics. So, weak acid, it can be either present in ionized form or it can be present in unionized form depending on the pH of the environment, pH of the medium. Unionized form is a form in which the carboxyl group is attached to the weak acid. RCOOH form. It is unionized form, and as I have told earlier that unionized form can cross the biological membranes easily. It is more lipid soluble. Ionized form in which the hydrogen gets detached, it gets deprotonated, so it is better cleared through the water solubility through renal system. It is the weak acids. Carboxyl group is attached, it is unionized form. When the hydrogen becomes detached, it becomes ionized form and it is more water soluble. Weak bases. Weak bases are in which the ammonium ion is attached. Okay, are NH3 positive. NH3 positive, as you can stress it, it is a positive sign. It means that it is ionized form of the drug. Ionized form are better water soluble and are better cleared, but when the hydrogen gets detached, deprotonated form is unionized form and it crosses the biological membranes easily. The examples of weak bases are morphine, local anesthetics, all the canes, okay, which are used in local in anesthesia purposes, amphetamines, and PCP. PCP is a phenylcyclidine, and it can be used as in the clinical vignettes. For example, the question can be of local anesthetic or it can be of amphetamines. So you need to think of weak bases because these are weak bases. Okay. Coming towards the graph, this is the first graph we are discussing, and there is no rocket science in discussing it. Just follow the um, terms which are labeled here. On the x-axis, this is x-axis, and this is the y-axis of the graph. X-axis indicates the term pH minus pKa. Okay, it means that if the answer pH minus pKa is in the x-axis, If the answer of this term is negative, it means that pH is lower and pKa is higher. So pH is lower, it means that acidic environment, as here -2, -1, these are more acidic environment. If the answer of this term is positive, it means that pH is more and pKa is less. So pH is more means that basic environment, here +1 and +2. So it is more basic environment and there was more acidic environment. Basic environment and acidic environment. Okay, so in the y-axis, these are written non-ionized form of the drug. Non-ionized form, I cannot stress it more. Non-ionized form mean that it is not ionized and it is lipid soluble. Lipid solubility is indicated in the y-axis, and on the x-axis, acidic and basic environments are indicated. Following the lines, this is a weak acid. Okay, in the top of the curve, it indicates that in an acidic environment, as you can see here, in acidic environment, weak acids are present as COOH form. These are non-ionized form and they are more lipid soluble. Coming lower, when we increases the pH, it means that environment became more basic, and the weak acid which was present previously in COO positive COOH form is converted into COO negative form, and it is more water soluble. So what is the thing here we need to understand? When we need to eliminate a drug, when we need to excrete a drug, when we need to eliminate the drug, when we need it to become more water soluble, put them in an environment which is opposite to their pH. For example, this was a weak acid. This was weak acid. So when we put it in a basic environment, it becomes more water soluble. It becomes more readily to be excreted. And this is a weak base. But weak base in an acidic environment is more lipid soluble, but weak base in a basic environment is more lipid soluble, but in an acidic environment it is more water soluble. The idea here is that let I clear it more. For example, this environment is acidic and this is a basic environment. Okay. For example, this is a COOH form, and here is also COOH form. Here is NH3 form. Here is also NH3 form. Okay. Understand that in an acidic environment there are a lot of protons. Okay, their protons are more, and in basic environment the protons are less. So when we put a weak acid in an acidic environment, it gets protonated, hydrogen becomes attached to it. Okay, and when we put a weak acid in a basic environment, because there are protons are less, so proton gets deprotonated, so it becomes like this form is present in the weak basic environment. Okay. Regarding the weak base, when we put it in an acidic environment, protons get attached and NH3 positive form is present. When we put the weak base in basic environment, because the protons are less, so it becomes deprotonated. NH2 form is present. Wherever there is a sign here, COO negative and NH3 positive, it is an ionized form, and these forms are more water soluble. But the stable forms, which are non-ionized form like COOH and NH2, these are lipid soluble. and they can cross the biological membranes. The acid, weak acid, is more lipid soluble in the environment similar to its own pH, and the weak base is more lipid soluble in an environment similar to its own pH. I hope uh, the concept here is clear, that when we need to eliminate a particular drug, either the weak acid or weak base, just put it in an environment which is opposite to their pH. For example, weak acid can be eliminated in the basic environment, weak bases can be eliminated or excreted in an acidic environment. Okay, here the same thing is written. For example, in a clinical condition or a clinical vignette, a drug is given whose pKa is 5. Okay, always the pKa will be given. The examiner will not ask to find the pKa, but like renal excretion and lipid solubility can be could be asked. And there is also written that the drug is weak acid or weak base. Either the examples are given. For example, weak acid aspirin, weak bases local anesthetics. So if the pKa is given, then draw the pH scale. It is a pH scale from 0 to 14. In the middle there is 7. Whether wherever the pKa sits, they draw a line in that place. This is a 5. So they draw the line at that point. So from 0 to 5, the pH is low, so this is an acidic environment. From 5 to 14, the pH is high, so it is basic environment. And the question also described whether the drug is weak acid or weak base. If the drug is weak acid, so in an acidic environment, as I have told you that in acidic environment the protons are more, so weak acid is present in protonated form, and the weak base is present in protonated form. In the basic environment where protons are less, weak acid is present in deep protonated form, and weak base is also present in deep protonated form. And both of the weak acids and bases are water soluble in an environment opposite to their pH. You can easily see here the weak base is soluble in water in acidic environment, and weak acid is soluble in water in basic environment. So understanding these concepts help you to verify whether the drug can be eliminated or it can be better absorbed. The last topic is the ionization. Ionization increases the renal clearance of the drug. Why? Because the ionized drug becomes more water soluble. Free and unbound drugs are filtered. Okay, filtered from the glomerular capillaries. Filtration occurs of the free and unbound drugs which are not bound to the plasma proteins, and whether the drug is ionized, whether the drug is non-ionized, both of them are filtered. Like you can see here in the diagram, ionized drug and non-ionized drug both are filtered, but only filtered. These are not reabsorbed. We'll see in a second. Only non-ionized drugs undergoes active secretion or reabsorption processes, because these two processes involve the biological membranes. Non-ionized means lipid soluble, and ionized form get trapped in the filtrate and it must be excreted. Here you can see that ionized form is excreted and non-ionized form can undergoes reabsorption and secretory mechanisms. So, clinical situation here is that acidification and alkalization of the urine. What means acidification of the urine? If we make the urine more acidic, it means that weak bases are more radially excreted, the opposite pH. If we made urine more alkaline, it means that weak acids are more radially excreted, opposite pH. You know, weak acids are more excreted in alkaline urine. What are the substances or molecules that acidify or alkalinize the urine? For the acidification, there are many, but ammonium chloride, vitamin C, and cranberry juice. For alkalinization purposes, we use sodium bicarbonate and acetazolamide. These are used for the acidification and alkalinization, respectively. The last a clinical correlation is hepatic encephalopathy. In hepatic encephalopathy, think about liver dysfunction. When the liver is dysfunction, it means increased level of ammonia. Okay. When we use a drug lactulose, it is a drug. The gut bacteria converts the lactulose into the lactic acid. It means that lactic acid causes the acidification of the fecal masses. When the acidification occurs, the ammonia converts into ammonium ion. Okay, acidification means there are more protons, so protons get attached to the ammonia and it decreases the ammonium circulation, which is very dangerous to the body. If there are high ammonium circulation, it can affect the nervous system, it can affect the cardiovascular system. So we need to reduce the circulating ammonia by acidification of the fecal masses by using the drug lactulose, which is converted into lactic acid by the gut bacteria. This was for today. I hope you understand the terms and clinical situations and the graph and the ionization concept. Just go through it once and you will be very cleared the revised things. Yes, and the next topic will discuss the absorption of the drugs. So this was for today and I will see you in the next video. Goodbye.